Section 11.4, chi-square distribution, goodness of fit test. And this example says, big corporate executives want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent uniformly during the week. To test this theory, a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed in the following table below. For the population of employees, do the days for the highest number of employees occur with equal frequencies during a 5-day work week? Test of 5% level of significance, n is equal to 60. Alright, so this is in the segment here of the goodness of fit test. In this example, we're looking at a uniform distribution, hence here by the terminology equal frequencies. So here I outline and state that this is for a, again, uniform distribution. In this case, with a 5-day work week, what we want to do is observe here, so the number of absences, these are from the managers here. This is our observed. Which also translates to the sample. What we want to do is figure out with this concept down here, just below this here on the table. This is called the expected. And so usually by percentage, that will reflect here, and that's normally what happens with the control group is represented by a percentage. So with the goodness of fit test, we want to test here, or the big question is, do the distributions match? And that's the purpose here of the goodness of fit test. So for this example, managers were asked on which day of the week that they thought that employees were typically called an absent. If we assume for a uniform distribution from the claim, then that percentage out of 100%, so we're looking at, I'll put that here, 100% divided by 5 for the 5-day work week would equal 20%. However, we need to get that translated into a sample size. So since we have a 60 manager sample, therefore, if we want to go ahead and do the same thing, like instead of divide by 5, or we can multiply times 20%, if we went ahead here and divided by 5, then we notice that that we get an even number across the board, which is going to be 12. So let me go ahead and grab a calculator here. Again, if you take 60 divided by 5, and you get that even number 12. So that's spreading that across evenly. Again, the only reason why I'm doing that is because they're wanting to state or show for a uniform distribution. That's not uncommon to do that for a goodness of fit test. A lot of other cases there are specified percentages for each category, but here they just want to even across the plane. So if we were to reflect for a sample of 60, then 12 would be the uniform number. And so that's always easily done by either two cases here, taking 100% and dividing that by the number of categories, or here in this case the total divided by the number of categories. And again, I want to specify you only do this when we're assuming a uniform distribution. All right, so I'm going to go ahead and erase up here. So these will be important numbers that we use up later. Let's go and fill in for the populations. So population number 1 is collecting those days of the week in which the managers thought that they were absent. So the number of this, so this is the set of all days absent for a 5-day work week recorded by management. For population number 2, we want to do the same thing, but in this case, this is by employers in general. So here it says here, so we're comparing that employers to, where is it here for the sample for the managers? Yeah. So the employers, or the generic employers, is for the control group. And more often than not, that if you see a list of numbers in this case, that is always going to be the observed, that is reflecting the experiment group, the first population. So for this, we want to set this out for the uniform distribution by the percentage here, and that's why I stated out that 20% for each category. That for each one of the days of the week, a variety of different ways you can do that. You can say P1 is equal to, the 20%. Again, that's 100 divided by 5. Then the next one, P2, would be equal to, 20%. And that P is representative for population proportion. So I'm saying by percentage, I want it to be evened out. So always the null hypothesis, in this case, there's no distinction. It's always going to have equality. But this time I want this to be equal because we're assuming a uniform distribution. So the third day of the week being Wednesday, actually the third day of the week of the work week is Wednesday. Here the next one here for Thursday, 20%. And here for the last day here for the work week again here at Friday at 20%. You can use subscripts if you want to do that, then it probably makes sense to do Monday, Tuesday, Wednesday, Thursday, Friday as subscripts. If you want to do that, it probably makes sense to, say that's M for Monday, and then this is here for Tuesday, and then the third one would be for Wednesday with that subscript. And that's only for you to make the distinction. There's no real reason to do that. Pretty much we kind of know what you're talking about. But for note keeping, it's not a bad idea to do. In some cases, for the null hypothesis, they just write out that it's uniformly distributed. But always for the research hypothesis, we want to show that's not the same as that. That something stands out to be different. In this case, probably the opinion of the management stands out to be different than that for the employers in general. Okay, so again, for the record, for the null hypothesis and research hypothesis, always equality for the null hypothesis and inequality or not equals for the research hypothesis. For the chi-square, the goodness of fit test, we'll never do a left tail, right tail. well, okay, not specifically that, but it'll never be, you'll never have anything with, in this case here, with less than or greater than. You'll never have that. It's always going to be not equals. The requirements here is each, so let's line it here for the different expected, that we want to show, so each value in the expected and that's concerning population number 2, in the expected is greater than or equal to 5. Kind of similar situation that we talked about going back to proportions where that product was greater or equal to 5, very similar here in this case. If I go ahead and line this up, we have Monday, Tuesday, Wednesday, Thursday, and Friday. Looking at the expected, each one of those values was 12. So let's go back over here for the expected. Again, assuming a uniform distribution, taking that total, dividing it by 5, we get 12. So for each one of these, for the expected is 12, and that does verify that each one of those has to be greater or equal to 5. So we have the green light on that. Again, if that was the case, that we didn't have that, we'd have to take a larger sample from the observed group. But now that that's stated, this would now imply that our sampling distribution goes along with a chi-square, and that's why this is also called, instead of the goodness of fit test, it's also called a chi-square test. Oh, sorry, chi-square distribution. Interesting, the chi-square is a special form of a gamma distribution. Not really a big topic, or I don't even think it's talked about in the textbooks. Not a lot of common for introduction to statistics book, but this is pretty much where the concept of degrees of freedom originated here. So when we start talking about that next door, that the degrees of freedom formula is going to be equal to the number of categories minus 1. So number of categories minus 1. That's the definition for degrees of freedom dealing with the this chi-square test here with the chi-square distribution. So let's go ahead and apply that next door over here. This is a generic right skewed distribution. As n approaches, gets closer to infinity, this will develop more of a bell-shaped curve to the right of 0. Basically what's happening is that it's called a chi-square, or x to the second power. The chi-square distribution is a sum of normal distributions, squared distributions. So basically what's happening is that, for keeping this short here, like the standard normal distribution, we have our, 1, 2, 3, minus 1, minus 2, and minus 3. When you raise that, kind of this concept, raise the second power, anything that's negative becomes positive, anything that's positive becomes still positive, and that's why we reflect here that everything will now start off with 0. So the chi-square distribution is a sum of squared normal distribution, or normal random variables. So let's go ahead and proceed here with this. For this test, for the uniform distribution, so we have our degrees of freedom. Actually, we got to look back up to here. The level of significance is going to be important. Let's go back to that level of significance. Where's yeah, there it is, right there. We have a 5% level. So let's jump back over here. 5% level. So alpha is equivalent to 5%. And of course, as a decimal, that would be 0.05. Degrees of freedom, as we mentioned, that's the number of categories minus 1. We have the five-day work week minus 1. We'll end up using 4. And then for all of these, always right tail. So right tail test. No matter what, if you're doing a goodness of fit test, you want that to be a right tail to try to disprove this concept of 0. So let me kind of point this out down here, that the idea of 0 means that we have, quote here, a perfect match. So what we want to do is prove it's not a perfect match. And that's what we're trying to do with a research hypothesis showing it's not equal to that percentages laid out, saying that it's not uniform. I want to prove that it's not a uniform distribution. So the further away you are from 0, the better chance you have to do that. You want to be on that tail side. And so in this case, the tail side, or that side, is directly on the right side. So another thing here to point out is that the peak here is at this degrees of freedom of 4. This will change slightly when we go to the F distribution, which is a ratio of 2 chi-square random variables. And then this goes out to positive infinity. So we're going to need to line up these numbers here. I'm going to end up taking the 0.05, the 4, and the bracket here facing to the right to figure out what that cutoff point is. All right, so let's jump back over to GeoGebra to do that. All right, choose the third one from the top, the chi-square. Our degrees of freedom needs to be 4. Right bracket, and then bottom right box is allowable significance. All right, there we have our cutoff point, 9.4877. So that's the cutoff point for significance. If we can be to the right of that number, we can prove that it's not a match. It's not a uniform distribution. Okay, so let's go ahead and record that and shade there to the right, representing that 5%. So this is right here, that's 9.4877. That's chi-square naught. That's our cutoff point, and then to the right shaded is the 5%. Okay, so let's go ahead and collect the evidence and see and determine if we can be beyond that point. But let's go ahead and look here for the sample. This is for the observed. So always at this step here, when we write down any statistics, that's going to reflect actually to the data itself. There's not per se a statistic collected with this, so maybe just look at the data for the observed. So going back to each one of our categories, Monday, Tuesday, Wednesday, Thursday, and Friday, those are described by the 60 managers. So for up there at the top there in the table, Monday was observed at 15. In other words, I'm saying that 15 managers said Monday was the most called in sick. Next day is, I'm sorry, not sick, but absent. I shouldn't have said sick. 12 for Tuesday, 9 for Wednesday, 9 there again for Thursday, and the last one there at 15 for Friday. So from this observation, does it appear that these are relatively uniform? It doesn't have to be a perfect uniform, but does 15, 12, 9, 9, and 15 look relatively the same? We'll answer that question just a little bit here. You just want to double check and make sure that your sum is equal to that stated up there above. They don't usually always say what the sample size is, but you just want to double check that for the records. So nothing really there to report other than that, and what we're going to end up doing is standardizing that sample coming right here next door. So let me go ahead and grab here Monday, Tuesday, Wednesday, Thursday, Friday. Let me copy that over. And then what we're going to end up doing is comparing that to both of those groups as stated above. We have, quote, the observed, I'm going to use the letter O, versus that for the expected for the letter E. So that's always the language used with the with the goodness of fit, observed versus expected. So the observed is the sample. And writing this out again, we got 15 managers said Monday, 12 said Tuesday, Wednesday's 9, and then Friday was 15. But as we calculated, we took the total there for the expected, and again, to be uniform, divide that, the 60 divided by 5 is 12. So 12 for each should have been evening out the playing field here. And again, if you add those all up, just to double check there, you want to make sure that both of those add up to the same number, to that sample size is 60. What we'll then do is just do this by hand. In the next step here, we want to subtract the observed minus the expected. Then what we want to do is raise that to the second power. So we'll square that number. And the last step is divide by e. And the reason why I'm doing this by hand is just to show you visibly what commonly calculators do to come up with these numbers. You can, if you want to, grab the observed and expected, and there's a lot of different statistical calculators out there that will compute and give you the chi-square value. Not too bad to do that by hand. So let's just do this by row here, outlining for the first row here for the 15 and 12. So all you have to do is subtract, raise the second power, then divide by e, dividing that by that answer, the squared value, by 12. So let's go ahead and grab a calculator here and do that. A lot of this that we'll probably do here in our head anyway, but let's grab a calculator and do this. So the first one here, we're going to take 15 minus 12. Obviously that's going to be 3. So 15 minus 12 is 3. Raise that to the second power. That's going to be 9. And then you got to divide that by 12. So that's the last step. Take the squared value, divide by 12, and then you get 0.75. All right, so that'll finish that for that first row there. Again, subtract, raise the second power, then divide by 12. And again, here you get 0.75. All right, so let's go to row number 2 there for the Tuesday group. 12 minus 12, pretty easy there. You get 0. 0 to the second power is 0. Then 0 divided by 12 is 0, making sure that's a perfect match. And that's why I'm saying there that if two numbers are exactly the same, that's iterating the fact there that a perfect match implies 0. So no change there for Tuesday. Let's go ahead and go back down here for Wednesday group. 9 minus 12 is, it looks like negative 3. But that's okay because we raise it to the second power, you get positive 9, and then 9 divided by 12, again we get that 0.75. Alright, let's go back to keep going here for Thursday there, same thing, 9 minus 12, negative 3, squared, divided by 12, 0.75, done. The last one here for the Friday group, 15 minus 12, I think we already did that one up at the top, and then you get another 0.75. Okay, so that will do that, and we are done. So let's go ahead and total up the last column, and that will give you the chi-square value. So 0.75 plus 0.75, you can easily see here you get 3.000, 3 across the board there. So that's our chi-square value from the observed. And just for the record, this is pronounced chi. Chi is an X letter in the Greek alphabet, but we know chi as X, or X is a normally distributed random variable. So here in this case, 3 is just short there of our peak. This is definitely closer to 0 than past that cutoff point. So we're not able to show it's any different. Therefore, by our assumption, we're assuming from the very beginning the null hypothesis saying that everything is uniform, and we were able to disprove otherwise. So this is a fail to reject the null hypothesis. Fail to reject the null hypothesis. So we assumed from the very beginning that it was uniform, and we did not have enough evidence to reject that from the sample taken from the managers. Let's go ahead here and find for the p-value. Nonetheless, you want to do the same thing and shade to the right here. And these are always going to be right tail. To the right of the 3.000, So let's go back to the GeoGebra calculator and do that. And we should get a pretty large percentage here. Okay, coming back over here, grab the chi-square. Okay, back to our degrees of freedom of 4. Right bracket again. This bottom box here in the middle needs to be our positive 3. Click on the bottom right box, makes that adjustment there, 0.5578. So that is to the right of our standardized value, 55.78%. That number definitely is not less than 5%, and then still proves it's a failed to reject the null hypothesis. So 5578 or 55.78%. So definitely not less than the level of significance there, and that proves they're failed to reject the null hypothesis. So this will do it here for this example with the goodness of fit test. By the way, I just want to make a note that it's a good idea to read through the book first on some of these theories. Definitely doing here the multivariate part to get a better idea and situate it with the different definitions in the book in this section 11.4. So as you're going through this, you kind of know the differences that I do between what we call uniform versus non-uniform and the formulas associated with that. Alright, so this will do it here for 11.4, goodness of fit test.